As the PID block is customarily used in the process industries, the derivative mode is based on the PV. Some control systems provide the option of basing the derivative on either the PV or the control error E. But even in these, the default is usually derivative based on the PV. This video explores these issues. In the previous video, the derivative mode was a result of projecting the PV one derivative time into the future. An alternative is to project the control error E one derivative time into the future. At a point in time, two items of information are available for the control error E: its current value, its rate of change, or DEDT. The current rate of change of the control error E can be used to predict future values for the control error. The projected control error E hat at one derivative time in the future is E plus T sub D DEDT. The issues that arise when computing dPV/dt also arise when computing DEDT. But for DEDT there is an additional issue. Specifically, DEDT reflects the rate of change of the set point as well as the rate of change of the PV. Except for abnormal events such as equipment malfunctions, abrupt changes in the PV do not occur in process applications. But abrupt changes of the set point occur routinely. In previous videos, the set point for the hot air temperature was changed from 210 to 220 degrees Celsius. This is an abrupt change of 10 degrees Celsius. The control error E also abruptly changes by 10 degrees Celsius. This has consequences on DEDT. A subsequent video examines the numerical issues associated with computing dPV/dt in a process environment. When derivative is based on E, this must be extended to encompass abrupt changes in the set point. For the moment, let's defer all of this to the subsequent video. To obtain the PID control equation, start with the PI control equation written in its customary form, but with E hat instead of E in the proportional term. Replace E hat by the relationship previously derived, specifically E plus T sub D DEDT. The terms are normally written in the order suggested by PID. The proportional term is E. The reset term is integral of EDT. The derivative term is DEDT. When based on the control error E, the sign of the derivative term is positive regardless of the controller action. The hot air furnace will be used to illustrate PID control with derivative based on PV and PID control with derivative based on E. The initial tuning of the hot air temperature controller is a controller gain of 1% to percent, a reset time of 1.5 minutes, and a derivative time of 0.2 minutes. This is PID control. The derivative is based on the PV, as will be confirmed shortly. Switch the hot air temperature controller to auto. Change the set point to 220 degrees Celsius. The response exhibits an oscillation that decays rapidly. Technically, there is no overshoot. The PV never crosses the set point. Switch the controller to manual. Place the simulator on hold. Change the hot air temperature controller configuration to derivative based on E. Open the configuration window. Select the Algorithm tab. As was stated earlier, derivative is currently based on the PV. The current selection for derivative mode options is based on process variable. Expand the drop-down list and select based on control error. Save the change. Return the simulator to run. Switch the controller to auto. Restore the set point to 210 degrees Celsius. Place the simulator in hold. The two responses are not exactly the same, but the difference is small. The difference is so small that it is of no significance in practice. However, a difference in the controller output, the yellow pin, is visible both on a simulation and in practice. With derivative based on E, a set point change causes a spike or pulse exhibited in the response for the controller output. These are visible in practice as well as on the simulator. The spike or pulse is short-lived, so the impact on the PV response is too small to have a significant effect. The next video discusses how the calculations for a PID block are performed. Some find the difference equations to be more informative than the differential equations we have been using.